In this video, we are going to be looking at a very interesting topic. Namely, we're going to analyze what is the effect of multiplying a matrix with a diagonal matrix. And it's going to lead us to some very interesting conclusions. Let's consider some matrix P given by certain columns. Let's say the columns of P are K1, K2, all the way up to some Km. So the matrix P itself is a, let's say, n by m matrix. What happens when we multiply P by a diagonal matrix? What is a diagonal matrix? A diagonal matrix is a matrix who has diagonal entries being non-zero or not necessarily zero, but the other entries being zero. And let's call the diagonal entries lambda 1, lambda 2, and lambda m. Of course, in a diagonal matrix, the diagonal matrix will be of a square shape, so it will be some m by m matrix. Otherwise, there will be no diagonal to talk about. So D is a n m by m matrix. And by the way I chose the dimensions of these matrices, it should be clear in which way I want to multiply them. Namely, I want to multiply them like this, P multiplied by D. What is this going to be? Well, let's try to compute. So, to do that, let us write out more explicitly what the entries of the matrix P are, or maybe what we want to do is to write the matrix P out in terms of the rows. So K1 all the way. So K1, K with the upper subscript 1, superscript 1 represents the first row of the matrix P, and the nth row is represented by K with upper subscript, in other words, superscript, Kn. On the other hand, the diagonal matrix we keep the way it was. So it's a matrix with whose diagonal entries are not necessarily zero, but all the other entries are zero. The way matrix multiplication works, when I have identified what the rows of the left-hand side matrix is that what I need to do is I need to multiply the rows by the columns, right? The rows of the left-hand side matrix needs to be multiplied by the columns of the right-hand side matrix. And specifically, if I want to think of the result of the product in terms of its columns, what's going to be the first column of this matrix, of the product? Well, it's going to be the entire matrix P multiplied by the first column of the diagonal matrix, but that's the same as multiplying so the first entry here is going to be the first row multiplied by the column, and of course, since all the entries in the column are zero except the first one, what's going to happen here is that it's going to pick out, maybe I should write it like this, it's going to pick out the first entry of K1 row, and all the others are going to be multiplied by 0 in the sum, so they're going to be taken away, right? For the second row, it's going to be the same thing. So K2, 1, because lambda 1, well, also there is a lambda 1 factor there, I forgot about that. And so for the second one, it's going to be the same. And the last one is going to be lambda 1, K, and 1. Maybe I'm not quite happy how I'm explaining this, so maybe it's better to look at a specific example to see what we're trying to do there. So let's say the matrix P consists of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And suppose we're multiplying this by a 4 by 4 diagonal matrix whose diagonal entries are 1, 1. Maybe I shouldn't use 1 all the time, so maybe 2, 2, 1, 2. And all the other entries are 0. To compute the first entry here, I'm going to take this row and multiply by that column, right? But since this column has all the zeros there, it's going to pick out the first entry there and multiply that by 2, so it's going to be 2 times 1. So that 1 there is the K11. So K11 represents the first entry of the row K1. Okay, what about the second entry here? Well, the second entry is going to be the second row of the matrix P multiplied by the same column. So it's going to be 2 times 2 plus 0 times 5 and 0 times 8 and 0 times 11. So the sum of these, but that's of course just 2 times 2. So we see here that the second entry here in the first column is going to be the same 2 multiplied now by the first entry of the second row. So that's K21. K2 superscript 2 represents the row, and so it's the second row, and subscript represents the column. So it's the entry which is exactly on this example is this one. So the second row and the first column. So you see the coordinates here is the second row and the first column, right? What about the last one? Similarly, this is going to be 2 times 3. And so my point that I'm trying to make here is that the first column of this is just the first column of the matrix P multiplied by that 2. And this also we can observe here. You can see that the column index, which is this the subscript, didn't change. It's all 1 throughout, but the row index changes. So this entire thing is obtained from the first column of P by multiplying each entry of it by lambda 1. But then of course lambda 1 can be factored out, and we'll get that the first column of this product is lambda 1 times K1, where K1 was exactly the symbol for the first column of the matrix P. And exactly the same pattern will work later on. So now if I want, let's say, to look at the second column, I'm going to be doing this with that, right? And so because of all the zeros here, I'm going to be picking out the second entry, multiplying that by 2. So that's 2 times 4. Then picking out the second entry there, multiplying that by 2. That's 2 times 5. And then 6 times, and then 2 times 6. So the pattern continuing, we'll have, for the third column, we'll have, now again, doing this, right? So for the third column, we'll have 1 times 0 plus 4 times 0 plus then 7 times 1. So you see it will be picking out the third entry and multiplying that by 1. So 1 times 7. And again, the third entry multiplying that by 1. So 1 times 8. And again, we see that it's the 1 times 9. It's the column, the third column that's being multiplied by that value there. And the same for the last one, which will be the last column multiplied by the value there. So it's going to be 2 times 10, 2 times 11, 2 times 12. So back in the general picture, what we're going to have here is that this pattern continues. So as we go from left to right, the subscript will increase. and at the end we'll have lambda 1 k 1 m, right? Because now it's the mth column, but it's not lambda 1 anymore. My apologies. It's going to be lambda m k1m, and here we'll have lambda m k nm. And so the columns of this product are lambda 1 k1, lambda 2 k2, and so on, all the way up to lambda m km. And now I don't have space to fit that in, so let me do some space creation methodology that can only be done on a digital device. So the last column there is lambda m times km. Okay, we made a big deal about this. What's the gain out of all this? Well, let's be a bit more patient. So the first thing I want to remark is that the matrix P multiplied by the matrix D is given by a matrix whose columns are the first diagonal entry of D multiplied by the first column of P, and it goes all the way, so that then it's going to be lambda 2, maybe include that case as well. So lambda 2 times K2, and all the way up to lambda n m times Km. And remember that the K1 up to Km stand for the columns of the matrix P. Okay, so a matrix multiplied by a diagonal matrix is given this way. Now let's denote that matrix by A. Actually, let's not. Instead, let's imagine that we have some matrix A such that A times P gives the same value. And specifically, okay, what will be A times P? Well, A times P will be a matrix whose first column is A times the first column of P, which is K1. And the second column is A times K2, and so on. And the last one is A times Km. Okay. If I have some matrix A and I multiply it by P, I get this result. On the other hand, if I have the same matrix P multiplied by a diagonal matrix, I get this result. Now, the reason why I went into all this is to come to the following conclusion. We can formulate it as a theorem that we're going to have, so first of all, let's clarify what the dimensions of things are here. Let's suppose that A is an n by n matrix and that P is an n by m matrix. Let me just check that's the dimensions I used there. Yes, it is. And D is an m by m diagonal matrix. Under these assumptions, so suppose this is so. Under these assumptions, it turns out the following: that A times P is equal to P times D if and only if, okay, let's see. What would it mean for the A times P which we've got here to be equal to P times D which we've got there? It would mean these matrices are the same. Now, what does it mean that the matrices are the same? It means they've got the same columns, right? Okay. That means that AK1 is lambda 1 K1, AK2 is lambda 2 K2, and so on, right? So if and only if AK1 equals lambda 1 K1, a k2 equals lambda 2k2, and so on, all the way up to akn equals lambda m km. Where the k's stand for the columns of P, so where P is the matrix given by k's as being its columns, and the lambdas stand for the diagonal entries of D. So lambda is a matrix with diagonal entries lambda 1 all the way up to lambda m. So initially we said lambda was D was a diagonal matrix, but we never specified in the formulation of the specific theorem what its diagonal entries are. So let's have a look at this theorem. This theorem is, of course, a direct consequence of the computation we just made, right? Namely, which computation? Namely, this computation where we said that when we start with a P matrix P and the matrix D, when we multiply them, P times D is going to be of this shape. And of course, A times P is always of this shape. And now, to say that these two are equal is the same as to say that they're equal column-wise. And that's what this theorem says. You see, the theorem says that this matrix equation is the same as the series of these matrix equations. Well, the reason why we are interested in a theorem like this is that, as you can see, probably already now, the series of equations we've got here, they are nothing but statements of some vectors being eigenvectors and some values being eigenvalues, right? So provided the k vectors are non-zero. So ak1 equals lambda 1 k1 says that k1 is an eigenvector of A with eigenvalue lambda 1, and so on. So we learned now a very nice and elegant way of writing down a statement about certain vectors being eigenvectors and certain vectors being certain values being eigenvalues as a single matrix equation, which is AP equals PD. So that single simple equation, AP equals PD, with D a diagonal matrix, incorporates information about M different eigenvectors and the corresponding eigenvalues of the matrix A. And that's going to be useful for later on for the theory of eigenvectors and eigenvalues, and specifically in the problem of diagonalization of a matrix. Okay, so once again, let's summarize what we did here. We saw that having an equality like this, AP equals PD, amounts to having a series of these equalities, which we recognize to be the equalities coming from the definition of the eigenvalue and eigenvector. And so this theorem then gives us a technique of encoding information about certain vectors being eigenvectors and certain values being eigenvalues for those eigenvectors, encoding that information as a single matrix equation of the form A times P equals P times D, where the columns of P are the eigenvectors and the entries in D are the eigenvalues, each eigenvalue corresponding to each eigenvector in the successive manner, right? If you look at this, these columns here had to be equal, right? And so you see that the first diagonal entry corresponds to the first column as the eigenvector. The second diagonal entry corresponds to the second column as the eigenvector, and so on. So the order in which the eigenvalues appear in the diagonal of D corresponds to the order in which the corresponding eigenvectors appear as columns of P. So that was the aim of the video, to explain how we can encode information about eigenvalues and eigenvectors into a single matrix equation.